All right, gang, here we go. This is for Physics Unit 7, Part 2. We're talking about wave properties. All right, so just a little heads up. This material here is really, really important through the rest of the next couple of units, which will last a couple of months probably. Okay, so it's all about wave motion, okay? And you spent some time in Chem 1 learning about wave motion. You probably learned a little bit about it during physical science, maybe in middle school or high school, okay? So a lot of this will be familiar, but obviously it's going to be a little more in depth with some new material, some new words you haven't used before, some new math you haven't done before. But the important thing here is that all of this stuff here is going to carry through for the next several weeks. Okay, we're going to be talking about, like after we finish talking about waves and their properties, we're going to move directly into sound. Sound travels as waves, so then we'll talk all about sound. A lot of sound's properties depend on the fact that it is a wave, right? And then after we finish sound, we'll talk about light, after light, okay? And light travels as a wave, right? So all of light's properties have something to do with wave motion and wave properties and wave interactions. So anyway, so this stuff is really, really important to make sure you have a firm grasp on. So make sure that you do your practice problems here and really understand what's going on. It'll go a long ways to helping you out. All right, so wave motion. So this is the general definition of a wave. Okay, it's a disturbance that propagates through a medium. Okay, so a couple of these words you probably already know, but then there's probably at least one that you haven't heard before. So a disturbance, okay, is something that messes with it, and you're at equilibrium, and then you do something to disturb that equilibrium or move that equilibrium to bring it out of equilibrium. So for example, when we were talking about pendulums, your pendulum wanted to be up and down at rest, and then you disturbed it by bringing it out of equilibrium and then letting it go, right? And it would fall back down and try to reach equilibrium again. Okay, so disturbance is just any sort of messing with your equilibrium. Okay, propagation is kind of an interesting idea. So propagates is any time that you have any sort of motion. However, it's special in that it's motion that continues to go on its own after it gets started. So for example, the easiest one that I can think of is the pendulum idea. Again, you've got your pendulum and you bring it up to disturb it, and then you let it go. And then your pendulum will go back and forth forever. You only had to mess with it to disturb it one time. And then that messing with it, that energy you put into it, continues to propagate that motion. And if it was a completely frictionless environment, that pendulum would swing forever, right? And it would continue to propagate, all right? So that's the definition of propagation. So propagation is things that tend to move, but they continually move on their own after you get them started. And then finally, through a medium, well, a medium is a substance that you're traveling through. Okay, so when I'm talking to you, okay, my voice is traveling through the air as a wave, and so the medium it is traveling through is air, right? And then so we can have all sorts of mediums that we travel through. If you take a rope and whip the rope, you create a wave in that rope. Okay, and that wave in that rope goes up and down, and the medium of itself, the medium is the rope itself. Okay, and so for example, each word we want to apply each word to a wave created when a child jumps into a swimming pool. Okay, so the child jumps into the swimming pool, so the act of the child hitting the water disturbs the water, and then it creates waves through the medium of the water, and then the waves propagate themselves out, right? And we've all jumped into pools before, and we know that those waves come out as circles from where they're at. Okay, a couple of things that you should know: mechanical waves require a medium. So mechanical waves are things like sound waves. When you take a rope and whip it, that's a wave. All right, those are mechanical waves. Electromagnetic waves are a special type of wave, okay, and they can they kind of create their own medium. All right, and they can travel through vacuum. And we make other assumptions about electromagnetic waves. For example, when we learned about them in chemistry, we learned that we can assume that all electromagnetic waves travel at the speed of light, just for an example of special properties of electromagnetic waves. All right, so now we need to talk about different types of waves. Okay, two things you need to know, though, is that number one, if a wave is started by a single disturbance, okay, it's called a pulse wave. So this guy was holding this rope, it was attached to some sort of wall, and he whipped the rope, wave gets formed, okay, and you just get that one wave. All right, so this would be a pulse wave. Okay, you could also assume that if the guy holding the rope moved it up and down over and over and over again, that he'd continually form these waves, right? And we would call these periodic waves. Okay, so periodic waves are caused by repeated disturbances. Pulse waves are caused by one single disturbance. All right, so if a wave begins with a disturbance that is single harmonic motion, remember that's what the SHM means, then the wave will be a sine wave. All right, so that's kind of our segue between what we were talking about mass spring systems and pendulum systems before, is that this idea that they create sine waves. And we used sine waves in order to graph the motion of both pendulums and spring systems. Okay, so if the wave in the diagram is moving to the right, in which direction is the red dot moving in each case? So let's look at this guy real quick. So it goes A, B, then C, D over here, and you've got this vibrating blade. So this thing just kind of wags back and forth, and the rope's attached to the end of it right here. And as it wags, this rope that's attached to it is tied down on some end that's cut off in the picture that we don't really see, and then the rope gets put into a sine wave, because this is simple harmonic motion right here. All right, and so this wave, you can imagine, is going to be traveling to the right. Okay, and so the wave is going that way. Now, the interesting thing is, when we're looking at this red dot here, what happens to this red dot? Well, if we took a ruler, okay, if we just tried to measure how far away the red dot is from the end of the rope right here where it's attached, you'd see in all four of these pictures that the rope is exactly the same distance away. Okay, and see how it's like half a loop and then two full loops. So like 2.5 loops, 2.5 loops, 2.5 loops, and 2.5 loops. And it's the same distance away, but that wave is traveling to the right in each of these pictures. But what's happening to our red dot? Well, the red dot only moves up and down from where it is, right? So it started here, and then as the wave comes through, the red dot moves up, and then as it swings back down, the red dot goes back to the middle, and then the red dot goes down to the bottom. Okay, and this type of motion is defined as a transverse wave. Okay, transverse waves are waves in which the particles move perpendicular to the direction of the wave. So this is the key right here. Okay, perpendicular to the direction of the wave. So, so just like this, the wave was going this way, right? But the particle motion was going up and then down, right? And so this here, this is a 90-degree angle to the motion of the wave. Okay, and so that gives us, the perpendicular motion of the particles in the direction of the wave. All right, so click on this guy here, this link here. I'll mouse over it again and you can kind of see it. You could also click on it if you have access to the PowerPoint through our Google Classroom or website. Okay, and then you can watch that video there. Okay, I highly suggest watching it. It's only a couple of seconds, but it's worth watching. They do a great job with a little graph showing exactly what's happening. Okay, and so here's our transverse wave, and we can see that we have lots of these things that we're used to seeing. We got the displacement here. Okay, you got your up and down motion, and then you've got your wavelength. Okay, from crest to crest or trough to trough. Okay, you could also measure it from origin to origin. You just got to make sure that it's the same repeated spot. So if you're going to start right here measuring your wavelength, you can't stop right here because that's only half a wave. It'd have to be this full wave because this is where it repeats again, right? Right here, all right, to right here. Okay, anyway, and then your amplitude is the height of your wave, right? So it's the height from the equilibrium point to the peak or valley, crest or trough, all right? And don't forget, so this is the symbol the text uses for wavelength. Remember, this is in meters because it's a length, and this is the symbol we use for amplitude. All right. Now, the next other kind of wave is called a longitudinal wave. These are waves in which the particles move parallel to the direction of the wave is traveling. They're also called pressure waves. Okay. So if you take this spring here, okay, and then here's a better example. If you take if you've seen one of those air guns, right, where you grab it and you pull it back and you let it go and the air pulse goes out, that's creating a longitudinal wave, because when you let go of the air, cannon, right? It shoots the air forward, and that air hits the next air, which hits the next air, which hits the next air. And so all this air kind of gets pushed together as it kind of keeps going until it hits whatever target you're doing. Your voice also does the same thing. As I'm talking, my vocal cords in my throat are vibrating and pushing the air molecules and creating vibrations in the air molecules, and the air molecules are coming out and they're moving like this, pushing against the air molecules next to it, air molecules next to it, air molecules next to it as it goes. Okay, until it reaches, well, in this case, it's getting recorded. Those shakes or those vibrations are getting recorded by my microphone and then transmitted to you via your speakers, But if we were talking in person, okay, then it'd be the same idea. I'm talking and the air molecules are moving this way until it reaches your ears, and it would hit your ears, and then your ears would be able to figure out, and then your brain would figure out the signal to figure out what the heck I'm saying, all right? So the interesting thing about longitudinal waves is that they're really based on the density of whatever it is you're traveling through. Okay, so for example, we already talked about your voice. Your voice is a longitudinal wave. So if you're talking, okay, so the pitch of your voice and the speed of your voice is dependent upon the density of whatever it is you're talking through. Okay, so if you've ever sucked on a helium balloon and then talked after you've had helium, you've noticed that your voice gets much higher, right? And that's because the density of helium is much less than air. There's a lot less particles for it to move through. Okay, but if you're underwater, for example, water, I'm sure you've been underwater and tried to talk to your friend. Okay, and as you talk underwater, you notice that the sound doesn't quite travel as you're normally used to, and that's because water molecules are much closer together and it's much denser than regular air. Okay, and we know water is more dense because it's a liquid, and liquids are always more dense than gas. That's kind of the whole point. All right. So anyway, so in this specific diagram, they're using a spring to represent density. Okay, and so this wave is traveling to the right. All right. Okay, or the left. You can't really tell based on this, but I'm assuming because it's x1, x2, 3, 4. Okay, and we're moving to the right. All right, so you can see how at x1 we've got a high density, and then x2 it's low density, x3 is high density, x4 is low density. Once again, I highly suggest just pausing the video, typing this link into your account or into your browser, just to give it an idea. All right, it's well worth watching, and the video of the spring going, it kind of makes it a lot clearer. All right, so there it is again in case you didn't watch it. Okay, now let's sketch a graph of density versus position. So we're just going to do the same sort of idea here. So this is going to be our density. All right, so there's our rho for density. Okay, and so this is our equilibrium line. Okay, this is where our line, this is at just normal. If your spring was just at rest, this is exactly how far apart all the coils are from one another. Okay, so at x1 we have a high density, right? So we'll draw a line up there for a high density. At x2, notice how it's much more spread out. So it's a low density. So we'll draw a little line down here for low density. Why are you doing this to me? All right. At x3, we have another high density, so we'll draw a line there. And x4, another low density right there. All right. And so you can see that we've got high density, low density, and we kind of go back and forth. In between those 2 points, we reach a point where it's kind of in the middle, right? So this is in the middle between those two. And so let's connect all these dots. So we just kind of draw it up like this, and then it comes down and connects with the low density, and then the high density, and then over here to the low density again. And you can see, even with my bad drawing skills, you can see this is pretty much a sine wave. It's pretty wild that even a longitudinal wave can be represented by a sine wave. The difference is, though, that it's represented by density versus or density versus position, as opposed to displacement versus position. Okay, but that's really the only difference. All right, now one more or a couple more things here. Wave speed. We want to be able to calculate how fast our wave is traveling through. Okay, so we're going to derive this real quick. Okay, so we know from way back in first unit, okay, that the velocity or the speed of whatever it is we're talking about is equal to the change in x over the change in our time. Okay, change in x over change in time, and we know that delta x is always in meters, delta t is always in seconds. Okay, so if we wanted to find the wavelength or the speed of a wave, okay, we can use these two ideas, wavelength and period. Remember, wavelength is just how long it is from crest to crest, and the period is defined as the amount of time it takes for one wave to go through, and this is just in seconds. So wavelength unit is in meters, and period wavelength or period unit is in seconds, right? So we could take our velocity, since it always needs to be in meters per second, right? This is in meters per second. We can throw in these new ideas. So the velocity of a wave would be the wavelength over the period, okay? All right, so wavelength over period, and once again, this is in meters, right, per second. Okay. We also know that period and frequency are inversely related to one another, right? In the last video, we talked about how period is inversely related to the frequency. So if we take this idea here, plug it in for our t value, we can see that the velocity of our wave is really equal to the frequency times the wavelength. Okay, so these two formulas, like you already have this one memorized, but these two formulas are the important ones that you can use to calculate the velocity of your wave. Now notice that this is interesting, that means that the velocity of the wave is really only related to the frequency and the wavelength. Okay, and so here's your formula for it. Velocity of a wave, or the speed of a wave, is equal to the frequency times the wavelength. SI unit is in meters per second because it's speed. Okay, all right. And now, one thing you want to keep in mind is that for any given medium that we're talking about, okay, so that specific medium, the speed is always constant, okay? All right, so your speed is constant for any given medium, so that means that if your F increases, your theta has to decrease proportionally, okay? And that makes sense because if this number gets bigger, but this number needs to remain the same, this number needed to get smaller, okay? So as frequency increases, your wavelength goes down and vice versa, okay? So that means the wavelength of your wave is determined by the frequency, okay, and then the speed at which it can travel through whatever medium you're talking about. So your speed can only change, okay, you can only make your thing go faster or slower if the medium itself changes, okay, so you can change your medium simply by changing temperature, okay, so hot air is much less dense than cold air, okay, and so your air travels much differently in hot versus cold air, or the speed of your wave travels much differently in hot versus cold air, okay, same thing with deep water compared to shallow water, and the temperature differences in the density also changes as well, okay. And this is another example that we just talked about, helium versus talking underwater. It's all about that density, okay? And so as we change that medium, our speed of our wave changes, all right? Last thing here for this part, okay, waves transfer energy, okay, and that makes sense. So imagine this, you've probably been in a pool, right, you're chilling in the pool, and some big fat guy jumps in the pool, creates a cannonball, and when the waves he caused hits you, it pushes you back. Now, why did it push you back? Why did you feel that? Okay, now think about it this way, okay, if you have somebody that jumps into a pool, right, so there's the pool, there's the water, this guy jumps in, when he starts up there, okay, when he starts up there, he's got all potential energy, right? And potential energy equals mass times gravity, okay? And he jumps in, and when he hits, as he falls, his potential energy turns into kinetic energy until he hits the water down here, and then he's only got kinetic energy at the bottom. He hits the pool of water, and then all of his kinetic energy, or most of it, gets transferred to the water, and this creates waves, right? And so the waves of the pool or the water start going out. Okay, now remember we just talked about these would be transverse waves because the motion of the particles is perpendicular to the wave motion. The wave motion is going to the right, but the particles are going to be going up and down, up and down. Okay, so remember these particles aren't actually what pushes against you, right? Because really they're just water molecules that are just really going up and down against your skin. They didn't push you. The energy from the push came from the potential energy of the man who jumped into the pool. Okay, turning into kinetic energy, which hits you, and then that energy the wave carried is really just the kinetic energy from the guy hitting the pool. Okay, all right. Now, wave energy depends only on the amplitude of the wave. Okay, energy is proportional to the square of the amplitude. Well, what does that mean? Well, that means energy, okay, is proportional to the amplitude squared. Okay, so this is an important formula as well. So really what we're saying is that as we increase our amplitude, the energy goes up squared exponentially. So if I double my amplitude, then I've increased my energy by a factor of 4. If I increased my amplitude by a factor of 4, then my energy increased by a factor of 16. Okay, so increasing your amplitude makes a big difference for your energy of your wave. And that's about it for part 2 of this unit. Do your practice problems. Once again, this stuff is very, very important, so make sure you understand all these nuances, different terminology that we've we've learned, so on and so forth. It's important moving forward that you understand this. So do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.